Back in Chapter 7 and Chapter 8, we learned all about atomic orbitals and how atoms store their electrons. So these are my orbitals like 1s, 2s, 2p, 3s, etc. So we spent a lot of time talking about those and learning how to write electron configuration, and it turns out atomic orbitals are great when you've got an atom by itself. But when an atom tries to form a bond and become part of a molecule, they're not necessarily that great anymore. So just because atomic orbitals work for an atom doesn't mean it's going to work well for a molecule. So an atom is perfectly within his rights to change his orbitals when he goes from being an atom by itself to an atom being part of a molecule. So the way that the atom does this is by forming what are called hybrid orbitals. Hybrid orbitals, really simply, are orbitals that an atom makes by mixing together its atomic orbitals. So let me get a pen out here. For example, an atom could mix together one s orbital and two p orbitals to make three new, what we call sp2 orbitals. We're not that original, so one s and two p's, that's where we get the name sp2 from. So these new orbitals are degenerate, meaning they all have equal energy, which is nice because previously the s orbital and the p orbital had different energies. So the atom just mixes together its orbitals to make these new hybrid orbitals, because the hybrid orbitals are better for bonding. That's it. That's the whole reason he does this. Better for bonding, gives him lower energy, and that's what he's after. There's some really simple rules for how my atom makes hybrid orbitals. First of all, we're going to assume only the central atom feels the need to do this. The outer atoms can sort of make it work with their atomic orbitals. The central atom is the one that really needs to try and accommodate multiple atoms around it, and so he's the one that's going to hybridize. The atom's not going to do more work than it has to, though, so it's only going to hybridize however many it has to. So what we can do is look at the Lewis structure and figure out how many electron groups the central atom has around it, and that's going to determine the hybridization. However many electron groups it has, that's how many hybrid orbitals it's going to make. So if it had 3 electron groups, it would want to make 3 hybrid orbitals. And the possible hybrid orbitals are these down here. So sp, exactly what it sounds like. We mix together one s and one p orbital. sp2 is one s and 2 p's. sp3 is one s and 3 p's, and then we run out of p's. We only have 3 p's, so after that we have to start adding in d orbitals. sp3d, 1s, 3 p's, 1d. sp3d2, 1s, 3 p's, 2 d's. Now what's important is that however many orbitals you put in, that's how many orbitals you're going to get out. So with sp, because we put in 1s and 1p, we're going to get 2 hybrid orbitals out. For sp2, we put in 1s and 2p's, so we're going to get 3 hybrid orbitals out. sp3, we put in 1s and 3p's, we're going to get 4 hybrid orbitals out, and so on. So this guy would be 5, and this guy would be 6. So however many atomic orbitals I put in, that's how many hybrid orbitals I'm going to make. Now notice, for these first 2 guys right here, I don't use up all my p orbitals. Well, those leftover p orbitals don't want to just sit around and do nothing, so what they do are form double or triple bonds. So for instance, let's say we had a carbon-carbon double bond here. Well, double bond implies there are 2 bonds there, so we have to ask, where do those come from? The first bond comes from our 2 hybrid orbitals directly overlapping here and forming a nice bond. The double bond forms from the fact that we have these leftover p orbitals sitting here, and these p orbitals are so close that their electrons are allowed to jump back and forth. So top and bottom, that together forms my second bond, and we call that a pi bond. Looks kind of like the symbol pi if you just look at the top of it. So when you have a single bond, that guy is just one sigma bond. That's just a directly overlapping bond right there. But when you have a double bond like we do here, you not only have that sigma bond, but you also have that pi bond. If you had a triple bond, you would not only have one sigma and one pi, you would actually have a second pi bond, this one coming in and out of the plane of the picture here. So you would have a second pi bond between the carbons. So what we can do every time we see a single, double, or triple bond, we can actually count how many sigma and how many pi bonds we have. Every bond has one sigma bond, and then any extra bonds are going to be pi bonds here. So really, the questions you get asked about hybrid orbitals are A, what's the hybridization of this atom? And B, how many sigma and pi bonds do I have? Figuring out the hybridization is really, really easy because, as I said, we just count your electron groups. So, depending on the number of electron groups, we can directly translate that to the electron geometry from the VSEPR theory, like we did before, and now, however many electron groups, that's how many orbitals I need to put in. So what I like to do sometimes is draw out my S and my P's and my D's, and let's say, for instance, I needed 5 electron groups. I would say, okay, I need 1, 2, 3, 4, 5 orbitals to accommodate my electron groups. So that would be sp3d. And we can see, indeed, that's the hybridization scheme that goes along with it. So once you count your electron groups, if you draw out this little picture here, you can just figure out how many orbitals you're going to need, and then you just write it out like that, and that tells you your hybridization. So let's look at a couple quick examples. Once again, I've cheated by actually drawing out the Lewis structures for you. You'll need to draw them out typically, but for our purposes, we'll just do this really quickly. So we'll start with O3. O3 has 1, 2, 3 electron groups. So if we're, what am I doing? 3 electron groups. So if we were just worried about VSEPR, we know that would be a trigonal planar electron geometry. And because it has 1 lone pair, that would be a bent molecular geometry. But we're worrying about hybridization. So 3 electron groups, if I draw my picture here, S, P, 5, D, I'm going to need 1, 2, 3. So his hybridization is going to be sp2. So simple. And I'm only going to worry about that central atom. If I had to count total sigma and pi bonds, each bond has a sigma bond. So I have 1, 2 sigma bonds. That's the symbol for sigma. And that leftover bond there is going to be my pi. So this molecule has 2 sigma bonds and 1 pi bond. And the oxygen has a hybridization of sp2. All right. Next example, CH2Cl2. So I've got 1, 2, 3, 4 electron groups here. So if you think about my S, my P's, 2, 3, 4, 5, and my D's, 1, 2, 3, 4. Okay, my hybridization is going to be sp3, because I have 1 S and 3 P's there. And all 4 of these are single bonds, so all 4 of those are going to be sigma bonds. So the carbon has sp3 hybridization, and my molecule has 4 sigma bonds. The last example here, we have 2 atoms to worry about. Just like with VSEPR, if we have more than one interior atom, we can do the same process for both of them. So we'll start with carbon. Carbon there has 4 electron groups, and therefore his hybridization is going to be sp3. Oxygen also has 4 electron groups, so his hybridization is also going to be sp3, because lone pairs also need an orbital, so they still count as far as VSEPR theory is concerned. If I count sigma and pi, I have 1, 2, 3, 4, 5 single bonds, so those are all sigma. Got no pi bonds in this case because I don't have any double or triple bonds. So carbon and oxygen are both sp3 hybridized, and I have 5 sigma bonds in my molecule.